Thank you very much for joining here. Let me introduce myself. I am a solution architect in the Programmable Solution Group in Intel, so the group working on the FPGAs. And why P4 and the FPGA? First of all, I don't know how many of you are the developers here, so trying to create the FPGA that for in any form, yes. So maybe one, maybe two. That's what I could say as the guy who is making the FPGA. We're using the tools. It's not so simple what you can imagine. Yes, as you can imagine from the guides what we provide to our customers. Yes, it's very need to have the really complex tool and very rare skills and in the market to create the FPGA. And the FPGA technology is that really powerful technology today to make very useful thing and so goal of the P4 and the FPGA and what we are doing together with our partner Netcope is to make programming of the FPGA as simple as possible. That together with our approach, we can generate the FPGA images, what is the base for the programming of the FPGA to program that card here, to program that card, what we have here in the extremely simple way, yes. You provide us the P4 code, which is really the 16-port which defines what we have inside of the card as the 16-port P4 switch. It is that everything what you need to do, and using our tools, using the Netcope tools, which is the web-enabled, called the P4 Cloud, we can generate the end image to the card. Yes. What you need to do to test this is just to program using the USB programmer and to program the FPGA alone. Not more skills is necessary from you. Yes, you must know what you want to do in the P4 and use our card to test it. Together, it is a big progress from the previous approaches, what we had, what we see from the FPGA, then we generating the RTL. Yeah. So together with the card, we're providing some set of the tools, what we are working with. One thing is the drivers, which are the P4 aware. We are working on the P4 enablement for the DPDK, and today, for example, we can use the P4 programs together with the, for example, XDP, Linux kernel XDP, and we can fit the Linux kernel XDP, the extended data path in the kernel using the P4 card. We also working on the generating the traffic and the test profiles. What also was mentioned by the guys from the Google how to test that, to make sure that we are able to test and validate correctly what we have inside of the P4. Yes, because it is it is very easy to create some P4 code. Very easy is to create something which forwards the packet, but how to check that it is working correctly as we expect. Yeah? So it's a very big topic what we are working together with our partners, and it is part of the to include the P4 community to make this happen. And what is the vehicle to test this? Yes. We as Intel, in the Q4 this year, we created the first card for the NFVi based on the FPGA. That's what means the production card for the NFVi from the Intel perspective. It is not the evaluation board. It is the production card, what you can put to your NFVi, for example, to the Dell server or the HP server, whatever. And this card could be managed, could be managed by the OpenStack, could be managed by the OpenStack Cyborg, for example, could be managed by the tools available from the Dell or from the HP. That it measures, the temperature is measured, the voltages are measured. It's fully monitored card that you can use, and it should work in your data center. Yes, this is not the evaluation card. This is the production card. Okay, how looks like the first proposal of our architecture, what we are doing into the FPGA today, yes? It is the first step, what we are presenting, it is that first step which is available today. But I want to fool you that we have the full P4 stack with every functionality. I just want to say what you can do today. Yes, it is you got the compiler and you can just make the use case. Yes. We have, as I said, we have the card which is defined the P4 as the some kind of the switches. Yes, we define the P4 program here as the some set of the small switches together. When we define the parser, match action table, and the parser inside of the P4. And we define here the inline architecture when every port what we use here in the card is processing the packet to the software. Yes, using this architecture what we call the inline architecture. What we accelerating by the P4 is just only the ingress part. Yes, from network to the software. Yes, the part from the software to the network is not accelerated, but I will present to you the tons of the useful use cases and very powerful use cases what you can use with this architecture. Okay, the first use case is that today, how to solve the problem of the, how to fit Intel servers with the application and how to fit the Intel server with the 100 gig traffic, yes. And we are not talking about the, for example, 4 times 25 gig traffic because it is the simple one. We have such ASIC, but how to fit using the 100 gig, a real 100 gig when you have the single MAC address and you're receiving from the switch, your data plane switch, the 100 gig traffic, yes. It is that very simple design what we are doing. It is the load distributor. We call this load distributor when we are providing to the application some numbers of the virtual function generated by the 4-gig card, which is the present, and the picture on the card. This is the something that is mounted together with FPGA. And we have here the setting the 100 gig. And as this is the UPF, we're making that something what is called the smart load balancing. The smart load balancing means, for example, the uplink traffic is hashed and provided to the queues differently than the downlink traffic, yes. For example, we're making distribution on base of the UE IP address, yes. So in this approach, we can achieve, for example, the way that the same UE traffic, downlink traffic and uplink traffic from the same UE as handled on the same core on the CPU, which makes us big savings related to the synchronization issue. That additional model, what we are working, what we can even provide a demo, is that, for example, we can have the feed the BPF programs and BPF programs inside of the Linux kernel, yes. The Linux kernel improved the performance today with the eBPF support. And with the eBPF, there is a need to make the eBPF working correctly. We need to make some operation, some logic, some lookups, and some pre-processing of the packets inside of the FPGA to making sure that the eBPF programs making the forwarding decisions out of the kernel are making decisions. Yes. This is the example of the existing framework, yes, what we can use in the kernel, and what we can, without any change of the line inside of the kernel, we can use our card to receive the data and feed this data using our pack card. The pack card, by the way, is the programmable acceleration card. Yes, it is the kind of the smarting provided by the Intel. Yes. Okay, the most important use case what we are working, and this is the target for us, is the solving the problem of the NFVi in the NFV infrastructure, yes. Today we can see, we can talk about the accelerators for the VNF, like the EPC, let's make a charging, let's make the BNG, let's make the PPOE accessing, yes. But in the data center, when we have the virtualized data center, and when we want to use something like the network slices, yes, when we want to use the server-based infrastructure and the server-based data center, we should have something between the application and the data center. This might be application like a router or the vSwitch, yes, which has the big set of the functionalities, what you can use to make sure that the traffic sent from the application, between the applications, between the VNFs or the part of the VNFs inside of the data center is going correctly, it is isolated. You can make a sharing of the server between the multiple applications. You can make sure that you can make live migration of the application between servers, yes. And how it is achieved? In today's data center, you are achieving this adding to every packet, IP tunnel, yes, the virtualization tunnel. Like, for example, VXLAN, like MPLS over GRE, like GNF, like MPLS over UDP. Yes, it has many ways to do this. And adding these tunnels makes the packets process in the line, in the wire between the network and the Tor switch and in the network are very complex. They looks like much complex than they appears in the application side, yes. And this complexity makes a lot of problems for the software processing. Yes, we call this one of the problems is problems of the multiple touching of the packet when the packet is going first touched by the virtual switch and next touched by the application. Yes, due to architecture of our Xeon servers and the cache architecture, that packets must be copy must be made between the different cores when the vSwitch is running and the router and the application is running. Yes, what makes the lots of performance problems. Yes, especially for the long packets. Yes, we're solving that. For example, implementing some NFVi part, full NFVi part. We call this one-touch approach. When the packet is touched only by the application, yes, to avoid that problems. And okay, this is that main use case, and right, the Peter will talk about the what kind of the NFVi use cases we are currently implementing, or we can very easily implement using our current approach.
My name is Peter. I'm from Netcope Technologies, and I will continue in describing some more use cases that we have developed. Inband network telemetry, that's very popular, and there will be another session diving really deep into this use case. Just briefly, it's about collecting end-to-end information from the data path. So in order to tell a story of the packet in the network, it answers several questions about what path the packet took, what were the rules applied, how much time it spent in the individual network devices, and what paths were overloaded. This is done by inserting special headers into the packet, and then also extracting them and visualizing them in tools like Barefoot Deep Insight. We did this use case or demonstration of this use case for FPGA-based programmable acceleration card purely in P4, so no FPGA development skill set was needed to achieve this. You can look at the code at GitHub. And not only that we did the INT, but we also combined it with some tunnel processing. So we created a demonstration which is kind of handling packets in the following way. At the beginning, we've got a simple packet. Ethernet, IPv4, TCP, UDP, and the payload. And we apply INT source, INT transit, and GTP encapsulation on that packet. So after this processing, which is described in P4 and runs in a FPGA card, we get additional IPv4, UDP, and GTP headers, which represent the GTP encapsulation. And we also get INT metadata and also the first hop information. Then the packet travels through the network, and if that network is P4 enabled or INT enabled, it will add additional information. It probably doesn't have a laser. It will add additional information, additional packet headers into the packet, the hops, which are on the slide. And again, when it reaches a P4 program device, in this case, programmable acceleration card with INT sync and GTP decapsulation, it will extract or send back to the network the original packet, and it will extract the telemetry report, which is sent then to visualization tool. Another use case that we looked into and implemented in P4 is a segment routing. So segment routing is a source routing technology which enables us to do service chaining to control the path of the packet through the network and add information or instructions to the packet so that the devices in the network will know what to do with the packet. And to implement this, we really need a data plane support. So what we have done is a P4 code, pretty straightforward. This one is rather simple, unlike the previous one. So this one sort of fits into 2 slides. And as you can see, P4 code is very straightforward. We define packet headers, we define parser, and then we define a few simple actions to perform segment routing transit functionality, which is responsible for rewriting destination IPv6 address from the list of extension, from the list which is stored in IPv6 extension header. And we also decrement let's say, an index field which says to the next device what item from the list to use. So what it does to a packet, as you can see, it rewrites a destination IPv6 address, which are those red rectangles just below that green line. And then also the segments left field gets rewritten to 15 so that the next device down the link will know what to do with the packet. Why we did this exercise, not only that this is something that we were requested by one of our customers, but also it nicely demonstrates the difference in the productivity of P4 as compared to traditional FPGA development languages. With P4, we did an analysis of how much time it takes for a P4 developer to create a rather simple implementation like this and we compared it with an implementation that would be done by a skilled HDL developer. So the difference is tenfold, and the difference in the lines of code is even more than that. It's 80 times or even 100 times less code in P4 than in traditional FPGA programming languages, which not only shortens the time to market, but also any type of maintenance, bug fixing, any type of revisions of the code for backdoors or anything like that, makes it much more simpler. How do we provide this technology? We have a service which is called P4 Cloud, Netco P4 Cloud, where you log in, you upload a P4 code, and then you either get a bitstream, which is a final firmware that runs in a FPGA-based card, or there's also an option to go into a netlist, which is more like a precompiled library that people can embed into their designs. For those who have seen how the usual FPGA flow looks like, this is a super simplification because you don't touch the synthesis tools. They are hidden. They run in the background in our cloud service. And to get from P4 code into an run-in FPGA firmware, we're talking about hours, unlike weeks or months if you do the regular P4 development, RTL development flow. So we see a great value of using P4, and it's also good to have an alternative, right? It's also good to be able to target different devices, not only switch chips, because there might be deployments where you may want a different size of a solution, and you may want to run at hardware-like performance and low latency, and use the same language that you use to program the pipeline in a switch chip or some other device. So to sum up, what are the key benefits of P4 for FPGAs? FPGA, it's an abbreviation for Field Programmable Gate Arrays. So now we're really getting a programmable pipeline for programmable hardware. P4 and its execution model, which is a packet processing pipeline, maps very well into an FPGA. For every P4 code, there is a different implementation. So you can consider the resulting firmware as a set of custom-built instructions, which are unique for or specific to that particular P4 code. So for every code, you're basically using all the resources efficiently, which gives you some dynamics, nice dynamics in terms of what you can do. It's possible to have a small number of large tables, and also you can have large number of small tables. So you can really go crazy with your P4 pipelines, their depth and complexities. You can also define parsers and deparsers of arbitrary complexity. The only limitation here are the resources of the FPGA, so the size of the device that you have bought and deployed in your environment. Which also kind of opens the next point. There's a flexible offering of FPGA chips. You can go from smaller devices with 10 gig support all the way to high-end devices with multiple 100 gig support. And not only the size of the device differs, there are also different memory options. So you can have a device which has a lot of on-chip embedded memory with very low latency, but you can also have a smart NIC or a programmable NIC that you have seen on the earlier slides presented by Mirek. And you can even go further than that. You can instantiate new functions into an FPGA through externs. So you can do things like encryption or pattern matching. All of these functionalities map really well into an FPGA. So thank you for your attention, and I'm looking for questions.
This question was on the telemetry slide that you were showing. You mentioned you are able to add some headers. Can we go to that slide?
Sure. It's going to take time.
Oh, okay. So you mentioned yeah. What is the NCAP method used here, and what is the additional time that takes if you were to do these telemetry operations?
Could you please repeat that?
You're adding headers, right? So what is the NCAP method used here?
What is the NCAP method used here? It's a GTP encapsulation.
Oh, it's on the GTP tunnel.
Right, right.
Okay. And what is the latency added when we do these, when we use FPGA?
So it's within the realm of microseconds.
Okay.
I can't give you a specific number because every pipeline, I mean, every P4 code represents a different pipeline.
Right.
So you can influence the latency by the complexity of the code. If the pipeline does only, for example, MAC address filtering, it's going to be below 1 microsecond or something like that. If you do more, the latency grows.
Or do you have any comparison with other devices that do online telemetry? Some kind of comparison?
No, sorry, no, we don't have the numbers.
I have a question regarding the two parts of the so when you started about talking about the VNF acceleration that enabled via the P4 programmability into an FPGA inline card. Again, let me repeat. The first part of the talk was alluding to VNF acceleration. Basically, you're adding VNFs and you offload the software forwarding into the FPGA card, given that you have a P4 programmability. I wanted to dig deep a little bit on this side. So let's say that the beauty about the NFVi is that you deploy a VNF that doesn't know anything about what is running underneath in the NFVi infra. Now you're adding a VNF and you're trying to really implement the forwarding function of that VNF inside the hardware. What kind of APIs that you're going to expose to the VNF, and whether this needs a collaboration from the VNF vendor himself, that they need to prepare the VNF to be able to utilize this hardware acceleration feature? Or how do you do this? And what do you do regarding runtime deployment of VNF?
Okay,
Thank you.
Let me explain this, how we are talking. We are working in the massive deployment using the Cyborg. When we creating the pair in the OpenStack, the VNF, which is, for example, the virtual machine, and the image inside of the FPGA. And inside of the description of the virtual machine, for example, using the heat or using some standard OpenStack tools, we can define, for example, the type of the interface. We call this host interface part. And we know, for example, the orchestrator will be create a part, download the image of the FPGA to the FPGA. We start accordingly, the virtual machine will be used, this special accelerator. Yes? So virtual machine is aware of the what is the accelerator type. That we are working, for example, there is a project which is called the Rocket project in the OPNFV, and the part of the Rocket project is the defining of the reference point VNF, which will be defined how we can recognize more details about how it is accelerator type and what the accelerator can do. Yes, we are assuming that today that that from the OpenStack point of view, what the virtual machine gets is just the PCI device, which, for example, could be the VirtIO, yes, or could be the Fordville SRIOV, yes. But what the virtualization function is, will be provided using some ETSI-defined interfaces, yes, what we work using the OPN VRocket projects, yes. So.
You basically require the VNF to change the EA description or XML description to make use of this accelerator.
Yeah, it is that VNF should be available, at least should be able to detect and initialize drivers in this, and should be aware that this accelerator is connected together, yes.
Okay, so let's thank again for